Hey guys, Al here, Vitalize Seed. So I did a video yesterday on wood ash, and I got a lot of comments and private messages discussing adding wood ash, and also some other comments in regards to other things that you could do to add to the soil. And one of the things that I want to explain, at least at a high level, is when we're talking about adding amendments to the soil, be it a food plot or a garden or a farm field, and we're talking pH and base saturations and all of these different things, we really want to have at least a high level or a macro level understanding of soil chemistry. In order to understand soil chemistry, you really need to have a high level of understanding what a soil colloid is. Behind me, this is the easiest image. There's a ton you can find. If you Google it, you can find a bunch of different images and diagrams and experiments showing adding a amendment to the soil, and then of course all the chemical reactions thereafter, and they kind of outline it. If you're interested in that, I recommend just doing a Google search or even a Google Scholar search on, maybe understanding soil colloids or something along those lines. But at a high level, what is a soil colloid? So soil colloid is basically, think of soil in layers, okay? And on these layers, this is kind of an above picture of a singular layer. You're going to have negative charges. As you see in these diagrams, it says high CEC. You can see all those negative charges going around the outside of the soil colloid. On the low CEC, you see less charges. Well, why is that? Well, there's just less mass for negatively charged ions to adhere. So a low CEC soil is more towards sand. So there's not as much clay. There's not as much mass there for negative charges to be there, which means there's not enough area or negative charges to attract positively charged ions. This is why on sandy soils, from a chemical structure and things, you're going to have a much higher likelihood of having things leach through the soil profile. Not only the fact that it's sand, right? We can imagine that visually, but also the fact that you don't have enough negative charges, or you don't have a lot of negative charges that are going to then hold positively charged ions. On the flip side of that, high CEC soils, so higher clay content, more area for negative charges. There's also typically higher organic matter there, which is going to have areas for negatively charged ions to then grab higher charged or positively charged cations, calcium, etc. So this is very important because, one, by understanding CEC and just this general concept of negatively charged spaces that are going to allow the adherence of positively charged ions, calcium, magnesium, potassium, etc., we get the general idea or visualization in our head as to how the soil chemistry and soil structure from a chemical perspective functions, because we can visualize how calcium, potassium, and other positively charged ions need that negative charge to adhere to the soil. And we can understand that CEC is somewhat predetermined by our soil type, right? And that's going to either allow or not allow a lot of negatively charged ions. Now, neither one is good or bad. It's simply what we're working with, and how we amend our soils or apply fertility is going to differ based on some of these conditions. Now, yesterday's video, I talked about wood ash. So wood ash, we're just, for talking purposes, we're going to assume that based on the wood ash and the ash analysis, it's high concentration of calcium carbonate. When you look at a CEC and there's a low pH, a lot of those negative charges are going to be held by a hydrogen ion. A hydrogen is a 1+ charge. So when we put calcium carbonate on the soil and it reacts, the calcium is not altering the pH. However, it is a 2+ charge, as you see in the diagram behind me. So regardless of high CEC or low CEC, it is going to push that hydrogen molecule off that soil colloid. It's now going to be free floating in the solution between the soil layers. As you can imagine, water goes through there, the physical properties of the soil are going to allow that to happen. Calcium is going to take its place in the soil colloid, which is good. We want calcium on there. We want to make sure we're balancing our base saturations. So it's going to allow actually a little bit of porosity. It's a larger molecule between the layers, having more calcium. Depending on your CEC, you can adjust that, and that's probably another video for another day. However, that hydrogen now is out there, and that carbonate element, so is calcium carbonate, is now free. Those two are going to connect in the soil profile, and that's where you get your neutralizing, that's going to increase your pH. So we have to keep this in mind, guys, because when you add things to the soil, you don't want to just make assumptions that there's nothing on the soil. The soil is alive, not only biologically, but you also have chemistry there that's based in the foundation of geological changes over time, right, over thousands of years and things. And you have, you're all the way down to your micronutrients, iron and things like that. So those are already in the soil. So we have to, we talk a lot about biology, and it's great. And much of this is biological, and you hear about root exudation, which, again, there's chemistry there, right? It might be biological chemistry, but there's chemistry there. There's acids that come out of the roots that help from a nutrient solubility perspective. So I don't like to get too into the weeds because I think a lot of people just are disinterested. But I want to highlight this because when we add anytime we add something to our soils, be it a synthetic fertilizer, an organic fertilizer, a lime source, a wood ash source, chicken litter, manure, it does not matter. We have to at least conceptually look at the soil is not some inert environment. There are already existing ions there. So when you add something, think about, is it soluble? How is it going to break down? What's its ability to break down? How is it going to interact with the things that are already in the soil profile? And when you understand that, at least at a high level, you'll start to ask yourself questions or try to understand, okay, is this going to change my base saturation percentages in my soil colloid, which is going to change my chemical structure of my soil? Is this going to interact in my soil that I better make sure I have good drainage? Because the reaction here, one example would be putting down elemental sulfur. People do that sometimes to lower pH because it'll actually convert to, I believe, sulfuric acid, if my memory serves me correctly, which is going to be pretty acidic. It's going to lower your pH. However, you don't want sulfuric acid to just be sitting on top of your soil. So that's the situation where if you're putting down elemental sulfur, typically that's done on lower CEC soils because you do need to ensure that you have that good drainage. That's just one example as to why we can't just say willy-nilly, wood ash for talking purposes, as yesterday's video, that's just going to go on every field, everywhere, my yard, etc. We got to start with a soil test. Look at pH, look at CEC, look at base saturations, and if you do feel like you want to add something, be it a synthetic, an organic, a foliar, this will give you a little bit better understanding as to not only how is it going to impact plant life, but how is it going to impact your soil structure. So hopefully that was a little bit beneficial. I hope I didn't confuse anybody, and hopefully you'll find that useful. Please share, comment, like. Check us out at vitalizeseed.com, guys. Get outside and enjoy the outdoors.